How do you do, ladies and gentlemen, and boys and girls? Again, I am Julius Sumner Miller, and physics is my business. And we come to another lesson, so to call it, on heat and temperature. And the title of this one is Thermometric Properties and Processes. Thermometric Properties and Processes. By that I mean, what devices are there? What actions of nature exist for us to tell the temperature of a system? First, I would remind you of what is commonplace in your life. A thermometer, a thermometer. Now, you know what a thermometer is. We have a long glass tube that has some mercury in it, and it is pumped down a little bit and sealed off. And then the mercury expands when there is a change in temperature. And so we say, first, expansion is a thermometric process or property. Expansion. In general, all things expand when heated. Yet it is interesting to discover in a later recitation by me that there are some strange things that do not expand when heated. And I leave it for the moment for you to think about a very commonplace stuff which does not expand when heated. Strange business. So expansion is a thermometric property, a commonplace one. What is another one? Electrical resistance. Electrical resistance is a thermometric property. Now I'm going to do a most remarkable demonstration, and here it is. Supposing I take a coil of wire and connect it in series with, say, an automobile headlamp, and then connect it, as we say, to some difference of potential, like a storage battery, a battery like in your car, and let me have the circuit such that the resistance of this wire and the resistance of the lamp filament is just enough to make the lamp light at normal brightness. Now what do? I am going to heat this coil of wire. That's my symbol for heat. It's a candle, you remember? I'm going to heat it. And what do we discover? An astonishing thing. The lamp gets dimmer, suggesting that the resistance of that coil increases with rise in temperature. Now, for those of you who plan probably to pursue physics further, I will write for you that the resistance at some temperature T is the resistance at 0 degrees times 1 plus alpha delta T, which tells us the behavior of that wire with change in temperature, and this alpha is a certain property of the wire. Let's go down here and see this, because this is a very dramatic thing. Here is the coil of wire, and here is the lamp in series with it, and here is a storage battery, and I'm going to connect this storage battery to the lamp, and you see the lamp lights at what we would call normal brightness. Now, supposing I put some ice on there. I put some ice. Dry ice would be better. We would see the lamp light ever more brightly, meaning that I have cooled the wire and therefore lowered its resistance. Now let us get a feeling for how bright the lamp is. I am going now to heat that coil from below, and I'm turning on some gas here. Now, if we can dim the lights perhaps in the studio. Notice the lamp is getting dimmer and dimmer and dimmer because its resistance is increasing. Let me show you quickly by cooling the wire. Oh, notice of course, the ice is being melted by that hot wire. Notice now how brightly the lamp burns, meaning that the resistance of a conductor increases with change in temperature or rise in temperature. A very interesting thing. Very interesting for you to pursue. This alpha is a certain property of metallic conductors. It is called the thermal coefficient of resistance, or the temperature coefficient of resistance. And it turns out to have a value about like this, .00366 ohms per degree centigrade. And so somebody says, Professor, what's all that number mean? And I'm going to tell you an important secret. That number happens to be about 1/273rd. 1 over, and somebody says, oh, that is astonishing, because 1/273rd is the temperature and pressure coefficient of gases, which means what? That electrons in a wire behave exactly like the molecules in a gas. Isn't that fantastic? I want to say that again. The electrons in a wire behave exactly like the molecules in a gas. Who would think that? So, electrical resistance. Another thermometric property. Here is a very strong magnet, and here is an iron bar, and obviously, the bar is pulled onto the magnet by magnetic forces. Now, what would I do? This has to be a virtual demonstration. Here is the horseshoe magnet. Here is the horseshoe magnet, and there is the bar. Now, if I were to do this experiment for real, what I would show you is this. I heat that bar with a burner, and lo and behold, as the bar gets higher and higher in temperature, the magnetic forces are less and less effective, and soon the bar would drop off. That reminds me to tell you, if you should ever visit a steel mill, you will see that when the huge steel slabs are picked up hot, they are picked up with tongs like this, like that. But later, when they get cold, they are picked up by an electromagnet. Do you see that when they are hot, they cannot be picked up magnetically? So, magnetic property is a thermometric process. Another one, thermoelectric power. Thermoelectric. You get the connection? Supposing I take any two wires, two different wires, say copper and iron. Connect one pair of ends, and then connect the other to an instrument which we call a galvanometer. This is an instrument for detecting the existence of an electric current. Supposing I heat this junction. Lo and behold, an astonishing thing ensues. There is an electric current in the circuit which is evidenced by a reading of the meter. Let me show you that. I have here two different wires whose junction is connected right here, and this instrument is a 0 centimeter, and I'm going to heat that junction with a match. Watch it. Watch it. Look at that. Look at that. Now, that scale there reads in electric units. That is, it reads amperes. I want you to see now a thermocouple junction which is connected to a thermometric scale which reads really in degrees. Here are the two wires, and there is their junction. I'm going to heat the junction, and you watch the scale as well as the junction, because another important thermometric property emerges. Watch it now. I'm heating it up here. And now if we can get a look at the scale, you see the scale is going up. The scale is going up. And indeed, this could well be reading, I think it's reading 1,000 now perhaps, if we can get a look at the scale. And so the temperature is going up, and the scale reads in degrees Fahrenheit, 1,000, and now it's about 1,200, and so on. And now, if we had sharpness of eye and could see in the darkness of this room the junction that I am heating with the flame, we would see another property. There it is, there it is. I see it very clearly. It is red. It is red. And I have suggested, I'm going to cool this off. Oh, there's a very good question. Why did that sizzle, and where did the noise come from? You see what I'm getting at, boys and girls, and teachers, and fellow Workers, whenever we encounter anything in nature, we should ask, why does it happen? So, the point I wanted to make is that this junction got red as the temperature got higher. So, I'm prepared to tell you that color is a thermometric property. Color. Oh, number 3 is thermoelectric. Number 4 is color. Oh, I left one out, didn't I? I left out magnetism. Magnetism is a thermometric property or process. Color is a thermometric property. Notice, physiologically, when a fellow gets very angry, his temperature goes up and it shows in the color of his face. But here is a better demonstration than that. Here are some colored sheets of paper. Red, white, green, pink, blue, and so weiter, and so on. Now, what would I propose as an adventure for our study of heat and temperature? Take such pieces of paper to the mountain where there is a fresh new bank of snow and lay the papers out on the snowbank. And lo and behold, what would you discover? In the sunlight, let us agree, we would discover that they sink into the snow at different rates. Why? Because they possess different radiation and absorption properties which are thermometric. And I hope you agree that the one that would sink the fastest would be the black. And the one that would sink the least would be the white, obviously. White reflecting all the radiation that falls upon it. Some more at random thermal expansion, about which I shall say more later. Here is a little array of 2 bulbs with a very volatile liquid inside, like ether or acetone, and the vapor of the liquid is in one vessel above the liquid and here in that vessel. Now I'm going to apply some heat from my hand. Watch it. Watch it. Now, the action is not very fast. Not very fast. I had hoped it would be faster, and I'm led to ask, why is it not faster? And the answer is, this little piece of apparatus has been lying here in the studio, exposed to all the radiation from these hot lamps, and so it has come nearly to thermal equilibrium with the surroundings and will not respond too much. But one last evidence of thermometric expansion. You know, if you live in cold climates like Minnesota or northern Canada, that if you have some milk and cream bottles left on your porch in the morning by the milkman, that you find them in a strange behavior at the top, suggesting that something has expanded when it got colder. About this we shall speak more another time when we speak about the strange properties of water. And I shall return another day.